Hi ladies and gentlemen, welcome to Chapter 2. We're going to start to take a look at systems of equations that we can solve using linear algebra. That's going to do two things for us. It's going to provide us with an opportunity to solve some very relevant systems, the types of things that are being used for machine learning nowadays. And it's also going to help to expand our understanding of vectors, vector spaces, matrices, all of the components that go into linear algebra. So we're going to start here with chapter 2 and a few caveats as we begin. Matrices in this chapter are square. So in chapter 3 we'll talk about generic systems of equations. Here we're going to talk about systems ax equals b where we have n equations and n unknowns. He starts right off the bat talking about the inverse matrix. We will get to the inverse matrix later in chapter 2, but what his point here is that in the situation where we actually have an inverse, which is a conversation we can have for square matrices, then we could be in a position to find the solution to ax equals b right off the bat. Even though we would never use the inverse to find the solution, we'll actually look at the way that we would find solutions in just a minute, but if it were there, then theoretically we could use the inverse. So then he talks about the whole idea of building an upper triangular system where U is his matrix representation for upper triangular. And then he continues on and talks about information down here associated with kind of the whole process. We're just going to take one piece at a time, and what I want to do is start with some examples that you are familiar with. Beginning here, we're going to take a look at a 2x2 system, similar to what you've done in the past, and let's just think about what you would do in order to find a solution for this. For example, we could multiply the top equation times 2 and then subtract it from the second equation. So we could multiply by 2, that would be a 4x1 plus 6x2 equals 10, and then we could subtract that, and we would end up with, of course, a 0 here. A negative 4x2 is equal to negative 4. And then we understand an idea that's called back substitution, where once we've reached an equation with just one unknown in it, this is easy to solve. This is just x2 equals 1. And then using that information, we can return to either of the other equations. For example, the top equation would be 2x1 plus 3 times the 1 we found equals 5. 2x1 equals 2, and we see that x1 is equal to 1. And so this is our solution. x1 is 1 and x2 is equal to 1. We can do this in general for 2x2 equations. Let's take a look at the next one. Same type of thing here. Again, we would multiply by negative 2 and add. And in this situation, we're going to end up with a 4x1 and then plus 6x2 equals 12. And we will subtract. Subtraction is actually a key idea for this, and so we're going to continue to try to keep in our mind. We understand that subtraction is just addition with negative numbers, but we're going to kind of keep this idea of subtraction in our mind. All right, so when we subtract here, what we end up with is, we end up with 0 plus 0 is equal to 3. The resulting equation is 0 is equal to 3. When does that happen? It never happens. The situation we've run into here is, there are no solutions to this system of equations. And we'll talk a little bit more about what that means. Let's take a look at the third example. Similar type of a situation. Again, we multiply by 2 and then subtract, and that gives us a 4x1, and then we have plus 6x2 equals 12, and when we subtract, we can see we're going to end up with 0 equals 0. And when does 0 equal 0? That's always true. This situation is always true, and the result then is that we have an infinite number of solutions. We have a situation where all of the solutions, because what you'll notice is these two equations are actually the same equation. The second equation is just the first one multiplied by 2. So any value of x1 and x2 that satisfies the first equation also satisfies the second equation, and those values fall along the line, and there's an infinite number of them. So we have infinitely many solutions in this case. So we have infinitely many solutions. And these are the three situations that come up when we're looking at linear equations. We either have one solution, no solutions, or an infinite number of solutions. What's important to realize is the situation that never occurs is the situation where we have two solutions. That can't happen. For example, y is equal to x squared minus 4 would have solutions at negative 2 and 2. So x would be negative 2 and 2. That's never the case when we have linear equations. It's not possible. And we can see very clearly that this is a nonlinear equation. It has a quadratic term in it. So that's an important distinction that will come up regularly when we're solving linear systems of equations. Let's continue on. We're just going to jump straight into section 2.1 here. The overview which he provides is actually fairly brief. He talks about how we're going to change this system ax equals b into an upper triangular system where we can apply back substitution, and that's his last note here is we're going to take u times x equals to c, and we'll talk about what the c is, and we're going to solve that using back substitution. So one more time, this chapter is focused on square systems. A is a square matrix n by n. And he walks through exactly what we just discussed, the fact that we have one solution, or we have infinitely many solutions, or we have no solutions at all. And those are the three situations that we come into, and it's easy for us to visualize those when we think about lines. What I want to do is talk a little bit about the matrix multiplication which we addressed previously, and how we can use that to do elimination. What we're going to do is we're going to look at what could we left multiply on this equation, and of course we would have to left multiply on both sides of the equation. We'll do it with the same matrix. But what we're trying to do here is we are trying to eliminate the 4. We want a 0 in that position. So what we're doing is we're taking the same ideas of what we did in our very simple examples, the first 3 examples we did, and we're going to apply linear algebra. So what we want to do is we want to keep the top equation. So remember, if I left multiply, that's a row on the left, and then I sweep that through the columns on the right-hand side. So in order for me to keep the top row, I'm just going to multiply by 1, 0, and that's going to preserve that top row. And now what I need to think about is, what do I want to multiply times the top row to create a 0 after I do my multiplication? Well, that's a negative 2, 1. Right? I'm going to take negative 2 times the top row and add it to the second row. So I'm going to take and multiply that top row by 2 and then subtract it off from the second row, and that is going to create my 0. So I'm going to do that to both sides. I have a 1, 0 and negative 2, 1. And when I do that, let me just write down the result here. We're going to end up, of course, the top is going to stay the same. It's going to be 2, 3. We're still multiplying by the vector x1, x2 is equal to, and when we do this multiplication, we'll have a 5. Now what we're going to do is apply that second row on the left-hand side. So we're going to multiply by this item here, and we're going to apply that through. So negative 2 times the top row gives us what we were after, and that's the 0. That's the elimination of x1 in the second equation. Then we're going to have a negative 6 plus 2 is a negative 4. And then on the right-hand side, we'll have a negative 10 plus 6, which is a negative 4. And what you'll notice is we have the same equations that we found in the first example. We have the top equation up here, which is 2 times x1 plus 3 times x2 equals 5. And then the second equation says negative 4 times x2 equals negative 4. This process then of elimination is something that we can standardize using matrices and vectors. All we're doing is using linear algebra to perform row operations. The 3-row operations that we can do are we can swap rows. Rows are just equations, so swapping them is no different than just rewriting the equations, which of course doesn't make any difference. We can scale rows. We can multiply a row by a constant. That's what we did here. We multiplied by a -2. And then the last thing we can do is multiply one row by a scalar and add it to another row, and that's what this row here is doing. It's multiplying the first row of the equations by -2, and then it's adding it to one copy of the second row. And that's what gives us this elimination down here. So all we're doing is taking these ideas, which you're familiar with, and putting them into the context of linear algebra. Once we have a system in this upper triangular form, doing the elimination, then we can proceed with back substitution. And I'm going to leave you to read this information. What we're doing is we are using the idea of back substitution. We'll work through an example of this at the end. Once we get to the bottom, we have an equation with one unknown, and we can solve for that unknown and then move back up through the equations to solve for all of the unknowns. He provides a conversation here. You want to make sure and read through this, talking about the elimination and then the back substitution and the entire process of how we want to make this work out. Again, he references the inverse matrices down here, because what we're doing through the process of back substitution is we're really solving this equation, which would be the same as left multiplication by u inverse if we knew u inverse existed. But that's a conversation that we'll have a little bit later. Just understand that's the idea of what we're doing with back substitution. All right, a little bit more formal conversation here about the elimination. And I'm not going to work through this example. This example is here for you to work through. I just want to talk about the idea. We're starting with this matrix problem, AX equals B. And I forgot an arrow over the top of that one. Remember, A is square. And what we're doing is we are going to apply elimination matrices to eliminate as we move through. So we're going to apply elimination matrix 2, 1 to the left-hand side and to the right-hand side. And let's just take a quick look at what that, remember, just as a reminder, the text is not here as a replacement for the string text. You need to have a copy of the string text. This is just here so we can reference part of the conversation. So what he's doing with the E21, his representation here is to say, hey, what do I need in order to eliminate and create a 0 where the 4 is? Exactly what we had before. This row is going to be -2, 1, 0, because he's going to take -2 copies of the top, add it to 1 copy of the middle, and add it to 0 copies of the bottom. And that's going to create this elimination. And obviously it has to be done on both sides of the equation. Then he's going to apply E31. As we discussed previously, this is easy to see if we think about taking this row and sweeping it through the rows of the matrix on the right-hand side. And all I want to do is point out the fact that he is next applying E31 to E21 AX, and then again E31, E21 B, and then finally E32. So E32, E31, E21 AX is equal to E32, E31, E21 B. And the result then, this is the upper triangular matrix U. And what you'll notice is we have not changed the solutions to our system. The row operations, which we talked about previously, are nothing more than the types of things we can do to equations. And as long as we do those operations to both sides of the equation, we can do whatever we want. So in this case, we have UX, and over here, we have the C vector. So the C vector comes from applying the elimination matrices to the right-hand side vector B. And you'll see that he actually combines, and we'll talk more about this in a couple of lessons, he combines these elimination matrices into a single elimination matrix E, so that EAX is equal to EB, where capital E is the product of all of these things. And as you've looked through the Grant-Sanderson videos, you'll notice that products of matrices are really function composition. The matrices represent linear functions, and when we multiply them times a vector, we are actually operating on the vector and mapping it to a different vector. So the combinations of the elimination matrices really is just the composition of doing several function applications one after another. And this is the conversation that he's having in here. Just make sure you read through this and understand the example that he's provided. Now he talks about, hey, what happens when things don't work out for us? First of all, let's define what pivots are. So the pivots are the values on the diagonal of the U. So these are the diagonal values of U, which is our upper triangular matrix. And what he talks about is the following. He says that we could get a 0. So when we do the elimination matrix and we create the 0 in the position we want, we might also create another 0 where we would prefer to have no 0. And that's his first example here. He's done elimination, but we have this 0 in a position where we would like to continue to do elimination. The problem is if we have a 0 pivot, we can't use that for elimination. There's no way to multiply 0 times a number and do elimination with it. So what we end up needing to do is the first row operation we discussed, which is swapping rows. Because again, that's just rewriting the order of the equations, no problem. What we would like to do then is we would like to take these two rows and swap them, because the 5 is a non-zero value that we could use for elimination. The way in which we do that is multiplication by a permutation matrix. This is a conversation for later in chapter 2, and we'll explain that. This is just an introduction. Again, remember the spiraling, talking about what we're going to explain in more detail in the future, reviewing the things we've talked about in the past. So he goes through and he shows us that after he's done the swapping of the rows, we now have a non-zero pivot. And if the values below the 5 were non-zero, we could use the 5 for the elimination purposes. The result of all of this is we have a system, still upper triangular, that we can use back substitution on. We just need to make sure that we've tracked what the changes in the rows are. But it has not changed the solution. When we do the back substitution, we find the solution. That is the solution. Swapping equations does not change the solution. Make sure you read through this, the conversation about being not full rank. This is a situation where we have a 0 pivot, but we also have a value below that, all the values below that are also 0. So there's no way we can swap a non-zero value into the pivot. This is the result of when we have no solution. We're not going to be able to solve this because we have no way of creating a non-zero pivot for back substitution purposes. And so he continues the conversation, and then he looks at dependent and independent columns. Remember the conversation about column space. If we have linearly independent columns, then those span the entire space developed by all the columns of A. If the columns of A are linearly dependent, then we actually have a reduction in the size of the vector space that we're spanning. One note that's really important here, triangular matrices, as long as the values on the main diagonal are non-zero, then those columns are linearly independent. And again, we'll provide the specifics of what linearly independent and linearly dependent mean. But this is an important thing for us to realize. If we have non-zero values along that diagonal, we have linearly independent columns. Otherwise, they're linearly dependent. He goes on to have the conversation geometrically about what it means to have a unique solution, the one solution situation, or no solutions, where we have, in this case, parallel lines that have no intersecting values, or an infinite number of solutions, where we have parallel lines, but they happen to be the same line. All right, what I want to do now is spend the rest of our time working through this example on page 45. So I've written this set of equations down. It's exactly the set of equations that he has here. And what we're going to do is just walk through this entire idea of how we approach these types of problems. And we'll talk more about this in the next lesson as well. What we're going to do, first things first, is we're going to write this in matrix vector form. So we want to be very comfortable with that. This is a 2, 4, negative 2, and a 4, 9, negative 3, and then a negative 2, negative 3, 7. That's multiplied times the vector of unknowns, x1, x2, x3, and that's equal to the right-hand side, which is 2, 8, 10. As we discussed previously, and now this is in the form, a x vector is equal to the b vector. As we discussed previously, the question is the vector b in the column space of A? If it is, then we have a solution. If it is not, then we do not have a solution. In the situation where we have a square A matrix, which is all of chapter 2, then if we have a situation where the columns are linearly dependent, then perhaps B would not be in the column space. If the columns are linearly independent, then they would span the entire space R3. And so B would necessarily be in R3, so we know we could find a solution in that situation. So now the question is, how do we approach this? We are going to do our elimination matrices in order to reduce this to an upper triangular system. Let me rewrite the matrix. All right, so what I've done here is I've created what's called an augmented matrix. And he references augmented matrix right here. It's when I take the A matrix, the coefficient matrix, and I augment the right-hand side vector on. The reason I want to do this is because for the matrix multiplication, instead of just multiplying on both sides of the equation, I can combine both sides of the equation into a single matrix called the augmented matrix, and then just do the matrix multiplication one time. So that's what we have here. We have this augmented matrix, and now what we want to do is we want to look at elimination. What is the matrix that we're going to multiply by to eliminate and create a 0 where the 4 is? That's my goal. So we're going to keep the top row. We're going to multiply negative 2 times the top row and add it to the second row. And then I would also like to create a 0 here. How would I do that? So for the third row, I'm going to take one copy of the top row and I'm going to add it to one copy of the third row. I'm really putting two elimination matrices together in this situation. When we do this multiplication, we're going to end up with, of course, that 1, 0, 0 is going to preserve the top row. This is just a 2, 4, negative 2, 2. Then we're going to take negative 2 times that top row and add it to the second row. That's going to give us the 0 we want. And then a negative 8 plus 9, and a 4 plus negative 3, and then a negative 4 plus 8. And then for the last row, we're going to take one copy of the top row and add it to one copy of the bottom row, which again gives us the 0. That's the whole reason that we chose the elimination matrix. And then we're going to have a 4 and a negative 3 is a 1, and then we're going to have a 5, and then we're going to have a 12. So this is what we have at the end of our first step. Now let me rewrite that matrix. So we have the middle of the process here. What we're going to do is we're going to apply another elimination matrix. This time our goal is to put a 0 here. The result then will be the upper triangular system that we're looking for back substitution. Well, we're going to keep the first row the same. We're going to keep the second row the same. Think about sweeping through. Keep the first row the same, keep the second row the same. For the third row, we want to take negative 1 times the second row and add it to the third row. So we want negative 1 times the second row added to the third row. And the result here then is Top two rows are the same. 2 and a 0, 1, 1, 4. And then we end up with a 0, negative 1 added to 1 is 0. Negative 1 added to 1, that's 4. And then negative 4 added to 12, that's 8. And now what we have is we have our upper triangular matrix. Just to orient you, what we have is this is the U matrix and this is the C vector. Because again, remember, they're augmented. We put them together. So the process, we created the augmented matrix AB, where we put in B as an additional column. Then we applied all of the elimination matrices, and the result was the UC matrix. Recalling, E is the product of all of the elimination matrices. And now, every row is an equation. It always is. So what we're going to do is we're going to take a look at this equation. That equation is 4 times x3 is equal to 8. So we have 4x3 is equal to 8, which means x3 is equal to 2. The next equation says x2 plus x3 equals 4. But we already know what x3 is. x3 is 2, so we put a 2 in here, and we see that x2 is equal to 2. And then the last equation up here is 2 times x1 plus 4 times x2 minus 2 times x3 equals 2. We substitute in again. This is a 2. This is a 2. And we end up with an 8 minus 4, which is 4. And we end up with 2x1 plus 4 equals 2. And when we subtract the 4 from both sides and divide by 2, we can see that x1 is equal to negative 1. So our solution is negative 1, 2, 2. Again, we'll do some more examples next time we go through this. But this was our goal, was to get to an upper triangular system so that we could then do back substitution. If we need to do row swaps, as we talked about, then we would end up multiplying by a permutation matrix, and we'll talk more about that in a few lessons. Let's take a look at today's questions. So these are the questions. Remember, we have a 3 blue, 1 brown video. For the first 7 lessons, we have at least one every lesson. Make sure you're keeping up on those. As you know from watching them, Grant Sanderson does an excellent job. And he's talking about, in this case, the extension of the idea of linear transformations. So the matrix multiplication with a vector is a linear transformation, and he's just explaining that more, and it's applicable to what we're doing when we are thinking about applying these elimination matrices to the equation AX equals B. That's it. Thanks, and we'll see you in class.